Good morning and welcome to all of you for today's class. Today we are going to discuss about the capacitance. Let us look at the definition of capacitance. Consider two conductors, namely M1 and M2. Assume that M1 carries a total positive charge of plus Q coulombs, M2 carries equal amount of negative charge minus Q. Except these two charges plus Q and minus Q, no other charges are present in the system, so that the total charge of the system is going to be zero. This plus Q and minus Q, which were shown here, they are in the form of a surface charge. So this plus Q spreads uniformly over the surface area of this conductor M1. Similarly, this minus Q spreads uniformly over the surface area of M2. Then the capacitance of the system is defined as like this. Magnitude of the charge on each plate, that is Q, divided by the potential difference between the plates, let it be V0. What is V0 basically? If you look at the direction of electric field is from M1 to M2. So if I want to move 1 coulomb of positive charge from M2 to M1 against the direction of electric field, what is the work done? The work done to move 1 coulomb of positive charge is nothing but the potential difference. Let that potential difference between M1 and M2 is defined as V0, which is nothing but the work done to move 1 coulomb of positive charge from M2 to M1 against the direction of electric field. So the capacitance of the system is Q by V0. What is Q? Magnitude of the charge on each conductor divided by the potential difference V0. Now let us find out the capacitance for some of the physical configurations. Assume that there are two spherical conductors, concentric spherical conductors. The inner one contains a total positive charge of plus Q coulombs. Let RA is the radius. So this plus Q spreads uniformly on the outer surface of this inner conductor. That means on a surface area of 4 pi RA square. And this minus Q is present on the outer spherical conductor, which has a radius of RB. So this minus Q spreads uniformly over the surface area of 4 pi RB square. Now what is the capacitance of the system? As per the definition, C is equal to Q by V0. What is the magnitude of the charge on each conductor Q? V0. V0 is the potential difference between the two spherical conductors. See, already we have the expression, we have derived an expression for V0. V0 is equal to Q by 4 pi epsilon naught 1 by RA minus 1 by RB. The potential difference between two concentric spherical conductors is given by Q by 4 pi epsilon naught 1 by RA minus 1 by RB. So V0 is equal to Q by 4 pi epsilon naught RB minus RA by RA into RB. So what is the capacitance of the system? Q divided by V0. So it is equal to 4 pi epsilon naught RA RB by RA minus RB. Now let us consider what is the capacitance that exists between two coaxial cylinders with radii A and B. Now assume that the radius A as well as the radius B of these two coaxial cylinders, the radius is very small. So the charge can be taken as a line charge. Whatever charge that is there on each of these coaxial cables, coaxial conductors, can be considered as a line charge. So the inner cylindrical conductor which has a radius of A, assume that it contains a positive line charge with a density plus rho L coulombs per meter, whereas the outer cylindrical conductor with radius B contains a negative line charge with a density minus rho L coulombs per meter. Now, how to define the capacitance of this system? The amount of charge present on each conductor depends upon the length of the conductor. So, in such cases, what we can do is capacitance per unit length is defined as charge per unit length divided by V naught. What is the charge per unit length? Because the charge density is assumed to be rho L coulombs per meter. So, charge per unit length on each conductor is rho L, and V naught is the potential difference between the two coaxial cylinders. For this also, we have derived an expression for V naught, rho L by 2 pi epsilon naught log V by A. So capacitance per unit length is equal to rho L by V naught, which comes to 2 pi epsilon naught divided by log V by A. Now let us consider a parallel plate capacitor. Suppose you got two conductors placed at Z is equal to 0 and Z is equal to D, and the area of each conductor is, let us say, A meter square. The plate which is placed at Z is equal to D, let us say, contains a positive surface charge with a density of plus rho S coulombs per meter square, and the one which is placed at Z is equal to 0 has a negative surface charge with the density of minus rho S coulombs per meter square. So the distance between the two plates is D meters. So now the capacitance of a parallel plate capacitor with A as the area of each conducting plate is given by rho S into A by V naught. What is the amount of charge that is present on each plate which has an area of A rho S into A? So rho S into A divided by V naught. What is V naught? The potential difference between the two conductors. Now if you look at the direction of electric field will be along minus Z direction. It is from Z is equal to D to Z is equal to 0, from the upper plate to the bottom plate. Assume that each one is of infinite surface charge. This is infinite surface charge. This is also infinite surface charge. So electric field due to infinite surface charge is rho S by 2 epsilon naught. So this creates electric field which is equal to rho S by 2 epsilon naught, and the bottom plate also creates the same amount of electric field. But because at any point between these two plates, okay, electric field gets added. So the total electric field is equal to rho S by 2 epsilon naught plus rho S by 2 epsilon naught. So it is going to be rho S by epsilon naught. What is the direction of this one? Minus Az. So electric field is given by rho S by epsilon naught. The direction is minus Az. Integral dl. So we have to go from Z is equal to 0 to Z is equal to D. So because we are moving along Z direction, dl becomes dz. So V naught is equal to rho S by epsilon naught integral dz means Z. Z varies from 0 to D. So this is the expression for V naught, rho S into D by epsilon naught. So the capacitance of a parallel plate capacitor is equal to rho S into A into epsilon naught divided by rho S into D. So epsilon naught into A by D. So that is the expression for the capacitance of a parallel plate capacitor. Now we can also verify that energy stored in a capacitor is half CV square. And because capacitor stores energy in the form of electric field, we are also having this expression WE is equal to 1 by 2 epsilon naught integral magnitude of E square dV. This is the general expression for the energy stored in electrostatic field. Now WE is equal to 1 by 2 epsilon naught. What is E? E is equal to rho s by epsilon naught. E square means rho s square by epsilon naught square integral dV. So what is the volume of this one? Area of each plate is A. How much volume it occupies? Because the space is D, so A into D is the volume. So ultimately WE is equal to rho s square into AD by 2 epsilon naught. Let us also find out what is half CV square. So 1 by 2 capacitance is epsilon naught A by D. V naught square. What is V naught? Rho s into d by epsilon naught. So this comes to rho s square d into a by 2 epsilon naught. Now you can see that the expression is same. We is equal to rho s square ad by 2 epsilon naught. Half cv square is also rho s square into ad by 2 epsilon naught. So energy stored in a capacitor is equal to half cv square.